So now I'm going to give a update on Pilot. And then the rest of the time we'll then run through an example and take questions. So what types of problems is Pilot designed for? It's designed for quasi-static modeling associated with earthquakes to answer such problems as what is the stressing rate on certain faults given the geodetic deformation, where is the strain accumulating in the crust, what is the slip distribution in an earthquake by using inversions from forward problems. Pilot doesn't run the inversion, but it'll do the forward problem in terms of Green's functions. It can answer questions such as how did the earthquake A change the stresses on faults X and Y. It can be used to examine different types of rheology and see which ones are consistent with observed post-seismic deformation, such as that from GPS records following earthquakes. One can look at different mechanisms for that post-seismic deformation by modeling the deformation through aseismic creep and maybe more distributed or after slip to see if that explains the deformation compared to viscoelastic relaxation. It can also look at dynamic modeling associated with earthquakes through forecasting amplitude and spatial variations of ground motion for hypothetical events, such as large scenario earthquakes. We can also try and look at past earthquakes, such as how the dynamic stress changes from an earthquake. How did those change the stresses both dynamically and statically on faults, on the surrounding faults. We can also look at the rupture behavior itself through the fault constituent models and spatial variation of those parameters to see if they are consistent with observed rupture behavior in a particular earthquake. Pilot can also be used for volcanic deformation associated with phenomena such as magma chambers and or dikes. One can look at inflation of magma chambers to try and constrain the geometry of the magma chamber and the depth to look at sort of the potential for an eruption. If there is an eruption, you can use Pilot to look at where the deformation might be occurring, what is sort of the ongoing potential for an eruption by looking at the depth and amount of material that may be moving within the crust, as well as dike intrusions such as the geometry and amount of material within an intrusion. Pilot has been developed by myself, Charles Williams, and Matt. We started about 6 years ago, I think. And our goal from the beginning has been to combine the dynamic modeling capabilities of EQSIM, which is a code that I developed in the late 90s, with the quasi-static modeling capabilities of Tecton, which Charles is one of the main authors. And so we had both of these were looking at earthquake faulting using finite element techniques, so there's a lot of commonality, but sort of different applications. And we decided that we would get farther by combining our efforts into a single code that we could expand and develop further capabilities to take advantage and leverage the efforts of putting things together. Our goal is to use modern software engineering, such as modular design, testing, documentation, and distribution to develop an open source community code. And hopefully this code will continue to live on and we can get additional contributions from the community. This is a diagram showing a typical workflow in a problem or research problem using Pilot. So we have the physics code here, with Pilot being a code developed by CIG that's open source. It uses a finite element mesh, so you must get that mesh from somewhere. Generally, we get a mesh from either from Qubit. Previously, we've worked with Legrit, which is a freely available a grid toolkit from Los Alamos National Laboratory. Both of those meshing packages generally want their information about the geologic structure from somewhere. There are two commercial packages that have been used by the community to develop geologic structure models, GoCAD and EarthVision. We have in the past done some work with TETGen, which is another mesh generation tool. It is open source. GMesh is another open source package that's been used by the computational seismology community, and we're currently investigating whether it can be used to generate the type of information that we can use in Pilot. That would give an open source alternative to Qubit for meshing. LeGrit is all command line driven. It's not really under ongoing development, whereas Qubit does, and Trellis, which is the commercialized version, are ongoing continued development, as well as GMesh. TETGen is maybe not undergoing continued development, but it is open source, so we can work with the source code. There are other alternatives. Relax, as we've mentioned. It's for simpler problems, but it'll compute the deformation much more efficiently because it takes advantage of those simpler physical properties. GeoFest is a code that was developed at JPL within the United States. It is open source. It's not highly developed and doesn't have quite the range of sort of types of problems that Pilot does. Abacus is a commercial file element package that some people use. It is much more expensive. Well, it's quite expensive depending on what type of licensing you have. And it's not open source, but there is quite a bit of extensive documentation. Once you've computed your problem with one of these codes, you then generally have to visualize it in a separate package. For Pilot, we generally use ParaView because it has a nice, simple user interface. Visit is another alternative that can read many of the same types of files that Pilot does. When you write to HDF5 files, you can visualize that within MATLAB. An alternative to MATLAB is Matplotlib, which is a Python-based tool for plotting. It's designed to look a lot like MATLAB, so if you know MATLAB, it's pretty easy to pick up on Matplotlib. And Relax generates both the VTK output that can be looked at in ParaView as well as GMT type files. So let's look at the governing equations in Pilot. We're solving the elasticity equation written here in equation 1. We have boundary conditions such as traction boundary conditions on surfaces S sub t written in equation 2. We have specified displacements usually on the boundary, but sometimes elsewhere in the domain. That's equation 3. And then we have relative displacement across fault surfaces written in equation 4. We solve this elasticity equation by using finite elements. So we first form the weak form of the equation by multiplying by a weighting function that's phi here and integrating over the volume. After some algebra separating the terms using the divergence theorem, some integration by parts, we have this integral over the volume of the stresses by the derivative of our weighting function. We have our traction boundary conditions, body forces, F sub I, as well as an acceleration term here integrated over the volume. We write our trial function and weighting function in terms of basis functions. Here are basis functions. We use n. And after some algebra and looking at isolating things for degree of freedom I on vertex n, we end up with equation 9. And this is what we want to integrate over our domain. And so that means we need to bring in our discretization scheme. This is a diagram showing how we sort of think about our meshes and our mesh data structures within Pilot. The top row we see the discretization of a triangular domain here, two triangles. And so we have two triangular elements. We have nodes 7, 8, and 9, and 8, 9, and 10. So those are our vertices are 7, 8, 9, and 10. There are edges within each of those triangles. So each triangle has 3 edges. So one triangle has edges 2, 3, 4. The other has edges 4, 5, 6. And we create cells 0 and 1. So triangle 0, and triangle 1 are made up of edges. The edges are made up of vertices. We have the same thing on the upper right for a quadrilateral mesh. We have 2 quadrilateral elements, 0 and 1. Quadrilateral 0 is made up of vertices 9, 10, 12, and 11. For cell 0, quadrilateral 0 is made up of 11, 12, 14, and 13. You'll notice here we've listed the edges. In many cases, we don't need this edge information, and so we can optimize the data structures and just store the vertices and cells. That's shown down here in the bottom. Makes our diagrams look a little simpler and also reduces the amount of storage we need. So for here, we'd have cell 0 is made up of vertices 2, 3, and 4. Triangle 1 is made up of vertices 3, 4, and 5. Same thing for a quadrilateral. We have our 2 quadrilaterals, 0 and 1. Quadrilateral 0 is made up of 2, 3, 4, and 5. Quadrilateral 1 is made up of 4, 5, 6, and 7. So with breaking up our volume or surface into elements made up of these triangular elements or quadrilateral elements, we then have those integrals. They now become sums over our volumes, and we use numerical quadrature to convert the integrals into sums over the quadrature points. So we have stress, derivative of the shape function, a weight here, as well as the determinant, the Jacobian of the cell that maps from our reference cell into our deformed configuration or mapped configuration. We have an integration over the surfaces with our traction, basis functions, weights, Jacobian of the cell. We have sum over the quadrature points of the volume for our body forces, basis function, weight, as well as the determinant of the Jacobian, and the same thing for our acceleration term. We want to form a system of algebraic equations. So we take all those integrals and we end up with the equation here 11 in terms of, this is now for a quasi-static solution, so we've thrown out the acceleration term because we'll neglect the inertial effects because things are occurring so slowly. And so we don't have to worry about the acceleration, which is essentially 0. So we have a matrix A, which is essentially the stiffness matrix, displacements, and then our right-hand side, which has all of our boundary terms, both prescribed displacements, traction boundary conditions, as well as body forces. And so our matrix A has the elastic constants Ci, J, K, and L. Derivatives are our basis functions, so these are basically the strain terms. Here, n comma L, n comma K, n comma J, and n comma I. And on the right-hand side, we have our what you would call our sort of forcing functions, our tractions, as well as our body forces. And we want to solve, we use a linear solver to solve for the displacement vector u. Now, when we have a fault, this is how we think of here shown as a slice through the middle of our sort of arbitrary volume. We have a normal on that fault surface that is picked based on sort of, it's essentially arbitrary. We can pick either pointing in one direction or the other, but we pick it based on the topology of the mesh. And so we have a positive side of the fault, which is the direction to which the normal points. So here's our normal vector down here in the bottom. it's pointing to the upper right. So we call this right side the positive side of the fault. That's sort of designated up here by SF plus. And then the other side is the negative side of the fault. And we have a relative displacement, one side relative to the other, and that gives us our relative displacement across the fault or our fault slip. And we have tractions that are applied on one side of the fault relative to the other, and this couples the two sides of the fault together. If we have a free surface on the fault, then it's essentially these decoupling of the domain. But of course, we want to prevent, if we treat it as a fault, we don't want to have interpenetration of the two sides. If we're treating it as a dike, we don't want the interpenetration. But in a dike, we may want opening. Generally, in a fault, we don't want opening because the overburden pressure keeps the fault closed. However, if the fault does come into tension, then with our fault constitutive models, we do allow opening. With this view of how we implement the fault, here is what it looks like, our traction boundary conditions on our boundary surface. We have the very same thing for our fault. So here, the traction on the fault I'm denoting by L, and that stands for Lagrange multiplier because we use Lagrange multipliers to constrain the fault slip. And as I show in a minute, so on our positive side, we have a negative sign for our tractions. On the negative side of the fault, we have a positive sign for our tractions. And that's just based on creating the tractions, giving the correct sign for our tractions to get the desired direction of slip. Then our constraint equation is our slip minus the relative displacement. When the relative displacement is the desired value, which is our slip, then we want that to be equal to 0. In the finite element case, we don't set that explicitly equal to 0. We set the integral over the fault surface with the dotted in with our weighting function equal to 0, as we would for our weak form for finite elements. This is, in our case of our faults, we actually use our numerical quadrature that with the quadrature points at the vertices of our fault elements, and so we end up actually enforcing this constraint condition to be exactly true at the vertices of the fault surface. We represent our displacements as a summation of basis functions, and we also represent our Lagrange multipliers and fault slip using basis functions. And so using this finite element approach, we have a rigorous mathematical formulation for how the slip varies as a function of space, as well as the tractions or Lagrange multipliers on the fault surface. And when we substitute that in, we get similar equations as we did for the traction boundary conditions and so forth on our fault surface. So we have basis functions dotted with each other, dotted in with the Lagrange multiplier. We also have our constraint conditions with our basis functions dotted in with the slip and dotted in with our displacement field. And so we end up, in the case of without a fault, we have AU equals B. When we add in the fault, we have an additional constraint equation, CU equals D. So that's our relative displacement equals the fault slip. And so we have an augmented system where we have our unknowns, our displacements, as well as our Lagrange multipliers. And so our sort of total A matrix for the system is composed of smaller matrices, our original A, the C transpose, which is essentially the direction cosines for the orientation of the fault, and then our displacements, Lagrange multipliers, our forcing function B, as we described earlier, and then our fault slip D. So here we specify the fault slip, we solve for the Lagrange multipliers, as well as the displacements. If we have spontaneous rupture or with a fault friction model, then our solution is a little different. We'll talk about this more in session 5. There we have constraints on the Lagrange multipliers associated with friction. And so in their case, we have to solve for both the Lagrange multipliers as well as a fault slip, and that gives us a nonlinear equation. So we use a nonlinear solver. In terms of how we implement this solution of the Lagrange multipliers and how we treat the fault, we do things a little different than many people do in finite elements that are traditionally done in geodynamics especially. So if our original mesh here was shown on the left side, if we sort of show what it looks like to the element by element, there's two nodes here in common between these two cells. So node vertex 3 or node 3 is shared by both elements. In implementing faults, what we do is when there's a fault, we insert additional degrees of freedom here for the Lagrange multipliers. And so if we show what it looks like in terms of topology, we have inserted vertex 9 and 8 in between vertices 3 and 7. And so we first add a vertex for the right side here that gives us a displacement. That sort of decouples the two sides of the fault. And then to do the coupling, we have add in this node 8 and 9 for the Lagrange multipliers. So this cell made up of vertices 3, 2, 6, 7, 8, and 9 is what we call a cohesive cell. It's complete. It doesn't take up any volume or any area, but it gives us a mechanism to implement those integrals that we just talked about in the previous slide. And so all of our equations here associated with the Lagrange multipliers and fault slip, those degrees of freedom in our system are associated with vertices 8 and 9, while vertices 3 and 7 are normal displacement vertices. The advantage of this approach is that the fault implementation is completely local to the cohesive cell, so the rest of the mesh doesn't know anything about the fault implementation or that it's even there. Within the solution, we get the tractions generating the fault slip. That's the Lagrange multipliers. We retain the block structure of the matrix, including the symmetry, and our offsets in the mesh mimics sort of a very small fine scale slip surfaces that we see on natural faults. There are two disadvantages. One is that we actually do insert these cohesive cells, and that requires adjusting the topology of fine element mesh. We do this within the PyLith code itself, so it doesn't mean you have to use a special mesh generator. We generate the mesh, but then just mark the nodes where the fault surface is. And then PyLith knows, okay, these are the nodes of a fault surface. It breaks apart the mesh, inserts the cohesive cell, and updates the topology. It also makes, with this slightly more complicated structure to our overall system matrix, it makes finding scalable preconditioners and solvers a little more complex. But that's where collaborating with computational scientists has helped us and gives us sort of these solutions to solving these problems, which come up similar to problems in computational fluid dynamics. So let's talk a little bit more about PyLith. The ingredients for running PyLith: you need the simulation parameters, you need the fine element mesh, whether it comes from Legrit qubit or just sort of some simple ASCII file that where you construct the mesh by hand. You need what we call spatial databases. These provide information about the physical properties, boundary conditions, and rupture parameters. Generally, these are simple ASCII files, but we also do support sort of interfacing with more complicated seismic velocity models. These spatial databases are how we specify a field or value in space. It can handle a uniform value, which you can think of it just as a single point in space, to specify the value being uniform. You can have a piecewise linear variation, such as that for attractions in a norm on boundary condition, or you can have something very complicated, such as spatial variation of the elastic properties in a seismic velocity model in 3D. One of the advantages of these databases, you specify the points that are independent of the discretization of the problem. So if you have a linear variation, you just specify those control points, and then all the values within the mesh are interpolated from those control points. So you can change the discretization size, you can change the type of cells without having to change your spatial databases. There are several types of spatial databases. There's a uniform database that allows you to just directly in a parameter file specify what the values are. There are simple databases, which are ASCII files that you can do 0D, just a single point, 1D variations, 2D variations, 3D variations, and then there's a special database for the community velocity model. This is an older version, 5.3. We've yet to update it for the latest version. There's also a special spatial database for Dirichlet boundary conditions or displacement boundary conditions where the displacement is 0. And this spatial database will basically set those displacements to 0. So you don't even need to create a uniform database. You just say, this is a 0 displacement database, and it knows, yes, I will set the value to 0. The features in our current version of Pilot. So this past week we released Pilot version 1.9. It's primarily a bug fix version, and we've updated a few things under the hood that caused sort of, if people were using extensions, creating their own extensions require changes, so that's why we said we incremented the version number to 1.9 from 1.8. It can look at, so Pilot can handle different time integration schemes and elastic formulations for implicit or quasi-static problems where we neglect the inertial terms. Pilot has formulations for both infinitesimal strains as well as small strains. For explicit dynamic problems, it can handle infinitesimal strains and small strains, and its formulation also includes numerical damping via a pseudo-viscosity term that cuts down the very high frequencies that the mesh cannot resolve. That's primarily for spontaneous rupture problems. There are a number of bulk constitutive models. There's the elastic models in 1D, 2D, and 3D. And in both 2D and 3D, we have linear Maxwell viscoelastic models, generalized Maxwell viscoelastic models made up of 3 Maxwell elements, a power law viscoelastic model, and a Drucker-Prager elastoplastic model. In terms of boundary conditions and interface conditions, we have time-dependent Dirichlet and Neumann or traction boundary conditions. We have the absorbing boundary conditions. We have kinematic, which are what we call kinematic faults, where we prescribe the slip on the fault. We can handle multiple ruptures on the same faults that are offset in time. And you can have different rupture speeds for each of those. We also have dynamic friction fault interfaces, time-dependent point forces, gravitational body forces. We have, when you use the dynamic fault interfaces, we have a number of fault constitutive models, including static friction, linear slip weakening, linear time weakening, and the popular Dietrich-Moreno rate and state friction with an aging law. And one of the recent developments in Pilot 1.9 is we've significantly increased the robustness of the explicit time stepping with rate and state friction. So those Pilot now provides excellent solution of rate and state friction in explicit time stepping schemes. So it already had worked very well for implicit time stepping, quasi-static problems, but now we've extended it to work well for the dynamic types problems. Other features of Pilot, we have automatic and user-controlled time stepping. This will continue to be an area of work in the future as we try and make it more sophisticated so that it really does adapt to the rate of deformation. You can specify initial stress and strain state within the model. We've discussed and mentioned various ways to get your mesh into Pilot. We have various output formats. These use BTK file formats or HDF5 files. VTK are ASCII files that are used with ParaView. You get one file per time step. A more sort of sophisticated binary format that works better in parallel are HDF5 files, where you can write out things like 3D arrays in parallel, so you get all of your time steps in a single file, so you can slice either along time or along space. And we can output the solution over a volume, solution over a boundary surface, solution at arbitrary points, output the state variables such as stress and strain for each material, the fault information such as slip and tractions. Pilot automatically converts units for all parameters, so in your parameter file you can say meters per second or kilometers per second, and those units will be converted to SI units and then non-dimensionalized within Pilot. We interface with both PETSI linear and nonlinear solvers and have developed a custom preconditioner that works with the algebraic multi-grid solver within PETSI to give variable scale, very good scalable performance within Pilot. Where Pilot is going, we're hoping to have version 2 available for this workshop. We're still finding some bugs, and so we didn't want to release it quite yet, but we hope to release it within the next few weeks. We may stick in some additional features that may take a little longer, so we may not release it till sort of the end of the summer. Under the hood improvements include a completely rewriting of the final element data structures. That is essentially done, and we're just debugging. One of the advantages of using these different data structures is that we have prepared for multi-physics such as coupling, heat flow, and fluid flow, as well as support for higher order basis functions. And that's sort of the main feature that we want to get in for version 2.0. And this would allow us to solve problems at a higher resolution for a given mesh by using higher order basis functions. So instead of just a linear variation of, let's say, the displacement within a cell, we could have parabolic, cubic, or even fourth order variations that then allows you to really sort of get that fine scale detail about the displacement and stresses within the cells. Obviously, that also increases the computational cost for a given resolution. But it does allow you, for a given mesh, to go to a much higher resolution, and you generally just use more processors to run a larger problem. Next up, in terms of improvements, will be version 2.1. That's looking at multi-cycle earthquake modeling. We really want to, this is one of our original goals for Pilot, and that's to resolve interseismic, coseismic, and postseismic deformation within sort of the single code at the different time scales. So have the propagating waves as well as the viscoelastic relaxation following. Longer term goals include multi-physics capabilities that we're preparing for now, such as coupling of elasticity with fluid flow and heat flow, and then scaling to larger problems. So really being able to look at some of these deformations at fine scale requires scaling to on the order of 1,000 processors or several thousand cores. So here's our rough timeline. We think our version 2.0 will be out later this summer, with version 2.1 the coupling in either winter or spring of next year. Then in the sort of all of 2014, probably October or November, we would have support for incompressible elasticity and our initial multi-physics aspects of heat flow and fluid flow coupled to elastic deformation. And then longer term, we'll look at sort of additional features, including finite integration on GPUs. So to accelerate our solutions even farther, make use of the graphics processors on people's computers. So quickly, we'll go through some of our design philosophy and start gearing up for looking at an example within Pilot. So we designed Pilot to be flexible and modular. We want to be able for users to be able to add boundary conditions, bulk constitutive models, fault constitutive models without having to modify the original code. We want the input and output to be user friendly. And we've when developing Pilot, we decided to make the top-level code written in Python, which is very expressive. It allows people to make their own modules without modifying the original code, because you can just add in these modules at runtime. But in order for fast execution, we've written the low-level code in C++. Pilot is the geodynamics part. There are a number of packages that Pilot depends on to provide other functionality. Pyre is how we get the input from users and handles all of our units, as well as a number of sort of the input-output features. It is MPI aware. There is Civ, our final data structures. They're part of PETSI. PETSI handles all of our linear algebra and solvers. It is parallel using MPI. It also depends on BLAS and LAPACK for some of its matrix operations. Our geographic projections come from the Proj4 library, as well as our final basis functions come from Fiat. And both of those take advantage of a Python library called NumPy, which provides access to arrays in Python consistent with C and C++. Pilot, when you sort of think about how Pilot is put together and how to specify parameters, you should think of it as a hierarchy of components. So there is and each component generally has a portion in Python where you get the user input. Then there is an interface layer provided by a tool called Swig, and then a lower level operations are done in C++. So some components that are very high level only have the Python part, but most have both a Python part and a C++ part that are then glued together using Swig. Here's what sort of our very top level code looks like in terms of a little cartoon. We have our Python Pilot app module that has what we call facilities or other components. So it has a mesh generator, has a problem, it defines the type of problem, and then an interface to PETSI. A time-dependent problem is a type of problem. There's also a Green's function type of problem. So that's sort of where this modularity comes in. A time-dependent property has a time-dependent problem as a dimension property. That's sort of the dimension is it a 1D problem, 2D, or 3D. It has a number of its own components or subcomponents that are labeled facilities. So it has something for non-dimensionalizing units called a normalizer. It has materials, boundary conditions, fault interfaces, a gravity field, and then the time-stepping formulation. So another example would be a prescribed slip fault known as our fault cohesive kin for kinematic. It has properties such as the ID of the fault, the name of the fault, a general up direction and normal direction that help define the orientation on the fault surface. Then it has its subcomponents called quadrature, earthquake sources, and output. In terms of example earthquake sources, we have our kinematic source, which has an origin time, so that's just a time when the rupture begins, and then the slip function that specifies the spatial variation and temporal variation of that slip time history. So let's look at a hierarchy of components for a simple toy problem. This is one of the problems that we'll run in a few minutes. So this is just a sort of rectangular prism domain where we're going to have Dirichlet boundary conditions on the two ends. I believe that's sort of plus x and minus x, and then roller boundary conditions on the bottom of the domain. When we look at that as a hierarchy of components within Pilot, this is what we end up with. So we have our application, we have our mesh generator. We're going to import the mesh from Qubit. So we have a mesh IO Qubit component that is a type of mesh importer that is a part of our Pilot application. We then have, we're going to run a time-dependent problem. We're going to non-dimensionalize our units using the elastic quasi-static non-dimensionalization. There's also one that is set up for dynamic problems. We have a number of materials. So we'll have a lower crust material as well as an upper crust material. The lower crust is going to be an elastic isotopic 3D as well as our upper crust material. Our output will go to a output matte elastic object, which will filter the quadrature point information through a cell filter average. That averages the state variables over the quadrature point, so we end up with a single value at the end that we can visualize in ParaView. Elastic properties are given by these spatial databases. Both the lower and upper crust will use a simple database, so that's shown here and here. Going back up to the top, we have boundary conditions. So we have an array of boundary conditions. We'll have an X negative, X positive, and Z negative boundary conditions. All three of those are Dirichlet boundary conditions that will be specified by simple databases. That's over here in the far right. Our problem formulation will have an implicit time stepping with a linear solver, a uniform time step, and then we'll output over both the domain and a subdomain. So that's here and there. So you can see how you can put all of these components together and develop, even for this simple simulation, because of all of our sort of flexibility in specifying the boundary conditions, it takes a fair number of components. And as you get to sort of more complicated simulations, you end up with more components, and you can swap components in and out. So that gives you a great deal of flexibility in setting up this type of problem that you have. The application workflow. So this is basically what the top level pilot application looks like. There's a main that says create the mesh, initialize the problem, and then run the problem. A time-dependent problem has a relatively simple interface. It's going to initialize the problem in the initialization, and initializes the time-stepping formulation. And there's just simply a loop that says, wow, that I have not reached the end of my time. Give me the time step that you want me to use. Then do sort of a pre-step part for sort of setting up the moving forward on the time step. Then advance the time step here in the formulation.step. And then perform post-step actions, such as updating our state variables as well as writing output. And if we look at what our formulation looks like for implicit time stepping, we have initialization. In our pre-step part, we're going to set the values of the constraints. In our stepping part, we're going to compute the residual and then solve for the displacement increment. And then, as I said in the post-step, we update the displacement field and write output. Another aspect of Pilot is the amount of testing that we do. So we have a test for nearly every function in the code, and we run these tests nearly continuously during development. This allows us to remove most of the bugs during the initial implementation, and then as we find bugs later, we create new tests that expose those bugs. So then once we fix them, it prevents bugs from reoccurring because we have additional tests to detect that type of error. And we generally run these tests whenever the code is changed, and that allows the code to continually improve. And we can actually, when we do optimization, we continue to run these tests to make sure that we don't introduce additional bugs as the code runs faster and faster. And of course, we run additional full-scale tests and benchmarks before we release. So let's end this sort of this presentation with some general numerical modeling tips. These work well not just for Pilot, but almost any modern computational code. Generally, we advise people to start in 2D if possible and then go to 3D. And the reason for this is that you can, in 2D, use much smaller problems, so you have a faster turnaround between sort of tweaking input parameters and looking at the results. It allows you to experiment with meshing, boundary conditions, solvers, etc. But obviously, it's important to keep in mind how the physics might differ in 3D, so that what you develop in 2D will carry over into 3D. We also advise, both in 2D and 3D, to start with a coarse resolution and then increase the resolution as needed. Especially in 3D, the problem size for any variation discretization size by a factor of 2, the problem size goes up by a factor of 8. That's nearly an order of magnitude, and that by doing a coarser resolution, you're going to end up with fewer degrees of freedom, so you have a faster turnaround time. It also allows you to, with a coarse resolution, experiment again with meshing, boundary conditions, and solvers, and then increase the resolution until the solution resolves the feature of interest. So the resolution is going to depend on your spatial scales and the boundary conditions. How much variation do you know in terms of the displacement field or attractions, your initial conditions and geologic structure? Is the geometry of the domain important, and at what resolution? You know, if your data is very sparse, and then it probably may not make sense to have things like topography if topography really isn't playing an integral part of sort of the deformation. Obviously, in volcanoes, sometimes the geometry is very important. But for a lot of earthquake-related problems, it doesn't really matter whether you have topography. It's going to greatly simplify how fast you can prepare your mesh and solve problems, and especially the meshing part. If you can remove topography and just have a flat surface, usually the mesh generation will go much faster. In some cases, you may need that topography. The displacement field, remember the displacement field is the integral of stresses and strains, and so if you don't really care about stresses and strains, and only you're going to say match GPS or seismic displacements, then you don't need to have high resolution in your strains and stresses. You just need the much smoother displacement field. So that being said, if you do want those, resolve those stresses and strains, it's going to take a much finer resolution. And always remember to use your intuition and try and use analogous solutions to check your results. Mesh generation tips. I would say our biggest tip is there's no silver bullet. It pays to experiment and try different techniques. There's no sort of single way to generate the best mesh. You can sort of take different paths between the two. For quasi-static problems, the hexes and quads are slightly more accurate and tend to run a little faster than types of triangulars. Elements, sort of the opposite is true for dynamic problems. It's very easy to vary the discretization size with tets, tris, and quad cells. When you have sort of a more structured mesh with hexes, it's more difficult. Obviously, you want to check and double-check your mesh. And when you're doing the mesh generation step, make sure you check to see if there are any errors. Look at your boundary conditions, such as your node sets and blocks, to make sure none are missing. Be sure to check your mesh quality. You want the aspect ratio to be as close as possible to 1. When you're using Qubit, in a number of examples, we'll name our objects and use the apropos scripting language that allows you to sort of take advantage of variables so that you don't have to keep retyping or changing the ID numbers or dimensions. And remember that the number of points in your spline or curved surfaces has a huge effect on the mesh generation time. So don't stick in a bunch of really high resolution contours unless you really need them. And we'll talk about this in the second session. So final tips: read the user manual. Don't ignore error messages and warnings. It's often advantageous to use an example or benchmark as a starting point. In quasi-static simulations, it's often easiest to start with the static part and then add the time dependence. And always make sure your solution is convergent at every time step. As soon as the solution doesn't converge, you may have significant numerical errors. In dynamic simulations, it's often possible to start with the static part and then go to the dynamics when you need it. And remember that the shortest wavelength of the seismic wave is going to control your cell size. And here's again, our CIG short email list, as well as the web page for Pilot user resources. Debugging tools, either covered in the manual, Pilot info with a script that dumps all the parameters and the current values to a text file. There's command line arguments, and we'll demonstrate how to use these, as well as the journal files. And finally, examples are in Chapter 7. If you're using the binary, the example files are in source/pilot/examples. If you're using the source tarball, they are in the source/examples, or some, I guess, just the examples directory. So that's it for the slides that we have, and we'll spend the rest of this first session looking at a problem. We'll run through Qubit, Pilot, and then ParaView. At this time, I think if anybody has any questions, feel free to type them in, and we'll take a look at that as we switch over to getting set up to run a problem for you. Are there any questions?
Seeing that.